All right, so after a little bit of delay, we'll finally get into this. Um, so just a little intro on me before I present all of this. I'm one of the organizers of the San Diego Machine Learning Group. I've been doing this for like 4 years now. Um, I work for H2O. I'm a Kaggle Grandmaster. I've been working in machine learning for a while now, but graph machine learning is actually pretty new to me. So I'll present this to the best of my abilities, and I'll explain the regions that I'm less certain about, and I'll try to give you the most accurate um, lesson that I can. But just bear with me. I'm not necessarily a pro at GraphML, but I am pretty well versed in general machine learning techniques. So in the past chapters, we talked about kind of just generally what are graphs for, and what kind of features can you extract out of them. And then this chapter will be looking at node embeddings and what you can do with those and how you create them, and all of the stuff related to that. So last chapter, Ted gave us a talk on traditional ML stuff. So we have this sort of pipeline where you have some form of a graph, and then you do some feature engineering on it. You do it at the node level, edge level, or graph level potentially, and then that yields you some features that tells you something about that graph. And then with these features, you can pass that to any learning algorithm basically, and then that will do some form of prediction. And you can do predictions at various different levels. So you can also do node level, edge level, graph level predictions. And so you can engineer your features accordingly. So then the kind of evolution of that is previously you would have probably engineered those features by hand. So you sit there and you go, okay, what is the metric that I'm most interested in for this downstream task? Do I care about betweenness or clustering coefficient or any of the other stuff that we looked at last week, or some other stuff that you could code up by hand? But this representation learning is kind of an automatic way to do that. You might not necessarily know exactly what's important, but you want to encode something that is relevant to the graph. And so you just kind of pass it to one of these representation learning algorithms, and it will generate features that are generally useful, that will pass to other downstream tasks. So our whole goal here is to take, at least in the beginning, is just to take individual nodes and then encode them to some vector. And that we'll learn exactly why we want to do that later. But just for now, understand that we've got this node U and we want to map it to some vector that becomes our feature representation and tells us about this specific node. So why would we want to do this? These embeddings can encode a lot of the information about it, so it can help you for downstream tasks like node classification, link prediction, graph classification, all of that stuff. So our goal is to get some mapping that makes a vector out of that original node and does something useful to it. So we could just trivially make a vector that's just 1, 1, 1, 1, 1, but that's not really useful. We want a vector that actually captures some sort of meaning of the node inside of that graph. And so here's an example of just a graph from Karate Club. And here's the graph as it's visually represented. And then here's a 2D embedding of it. And we'll learn more about this embedding. So you can just imagine this embedding has two different dimensions. It's got its X and its Y. And the characteristic that we're really looking for is we want similar nodes to occur in similar places within this 2D space. And so we kind of get that here where all of these ones are grouped up pretty close, and then all of these are grouped pretty close, and we'll learn more about those properties on later slides. And just as a side note, I'll stop periodically for questions if anyone wants to jump in, but also if you're unclear about anything or you want to add a comment, feel free to jump in. So to this point, does anyone have any questions or want to jump in with anything? All right, we will move on then. So the structure that we'll be looking at is this kind of encoder decoder setup. And so we'll kind of build this piece by piece. So we've got some graph G. It's got a set of vertexes. So that's this 1, 2, 3, 4. That's all of the vertexes or nodes that we have. And then we have this adjacency matrix. And this adjacency matrix is telling us their interconnectivity, basically. So we can see that 1 is connected to 2, and it's also connected to 4. So this adjacency matrix shows that it's connected to 2 and it's connected to 4. And then we can go down to 2 and we can see that 2 is connected to 1 and it's also connected to 4. And so this is 1 and 4. And so we can see that for all of the different nodes, we have all of the different interconnections. And it's this kind of sparse representation just showing which 2 are connected to each other. And so this is a very simple view of this. We're not including any other features or information. It's just basically, are they connected or not? And this is good for the undirected graphs. And it becomes slightly different if we're doing it on directed graphs or we're included other feature information. So the whole motivation behind doing this is to actually make it so we can take node U and node V, and then we can encode them in some embedding space, and that will put them in places that are close to each other. So if U and V are similar nodes, then we want them to show up close to each other. And so we have to find some encoding function that maps U to Z of U in this embedding space that puts them close together. And then in theory, we can tell which nodes are similar to each other and which ones are different. And then we can use that information, the encoded information, to do something useful with them, like classify them or do various different tasks. So there's various different things that we need to define. This is kind of just a general premise of, we've got node U and we want to embed it in some way, or encode it rather. And so we need to figure out how exactly are we going to encode this. And then at the same time, I was mentioning we want similar things to end up in similar embedding space, but we have to understand, what do we mean when we say we want U and V to be similar? Or maybe we don't want U and V to be similar, depending on our similarity metric. So then on the, we have those various different pieces to define. So the encoder is what maps from the nodes to embedding. So on the previous slide, we had node U. We want that to then become ZU, and we want that in the embedding place somewhere. And then we also have to define the similarity function. So that's what I was telling before, is, are U and V similar or not? We have to make that distinction in some way. And then we also have to have a decoder, which I think it's not even shown on the previous slide actually, but this decoder part is taking these embeddings for ZU and ZV, and then it's telling us, are these similar to each other? So we take the encoded embedding, and then we have to make this decoder step that's telling us specifically these two embeddings are close to each other. And so the whole goal here is to make it so that these fall on similar embedding spaces, and then in turn we want it to be that our embedding similarity is close to the similarity that we want to represent here. So basically we have this encoder, it maps to a low dimensional vector. So for example, we have node U, and then that becomes node U's vector from this encoder. And it's of D dimensions, and D is just whatever we decide to embed it as. So we can have that be 10 or 50 or 100 or some other number. It's whatever the size of the embedding we want it to be. And then looking at the similarity function, we have to figure out what similarity we want to represent, and we'll look at how we do that on a later slide. And then, like I was mentioning, this is the decoder step. The ZV transpose ZU is the dot product of these two embeddings, and we want them to show up as highly similar when our similarity function says that they're similar, and we want them to not be similar when the similarity function says that they're not similar. So we'll start by looking at the shallow encoding step, and this is what we'll use for the rest of it. But in later chapters, we'll look at things that are a bit more that are deeper. So the simplest possible approach is you just embed every single node as its own vector. So it's just a big lookup table, basically. Here's the math behind it, but I think it's easier to just look at this image, basically. So we have this massive embedding lookup, and it's this huge matrix where we have one column for every node. So say that we have a graph that has 1,000 different nodes. This is going to be 1,000 different columns. And then we also have the size of the embedding. So this is just something that we determine on our own. So we can say that it's 50 or 100 or whatever. So this would be an 1,000 by 100 matrix. And then when we want to pull out the representation for an individual node, we would just say, oh, this is node 100. So pull column 100 out of this big matrix. And so all of them are kind of learned independently. It's just one matrix. There's not really any representation or interaction between them. They're all unique. And then eventually we want to learn which ones are close and which ones are far away. So to start up, each of them is given just kind of a random value, and each node is just given an index, basically. So back here, we're just saying, okay, randomly, this node we picked is going to be 0, 1, 2 through n, however many nodes we have. And so there's a bunch of different metrics. We'll be looking at deep walk and node to vec in this one. So the kind of putting together all of the pieces, we had this shallow encoder. That's just that big embedding lookup I just mentioned. And then we have the parameters we want to optimize, which are actually the values within that embedding. And we'll look at deep encoders later, but not this week, basically. And then we can do various decoders, but in general, it seems like we'll just be looking at the dot product here. And so our whole objective is to make it so that the vectors for nodes that are close end up close in this embedding space. So looking at how we define node similarity, there's a bunch of different ways that we could do this. So directly, are they neighbors? So like in this graph back here, we could say, okay, U and V, they're neighbors, so they are similar, or various different things like that. So there's a bunch of different ways that you can characterize it. You can use some of the different things that we learned in previous chapters, like clustering coefficient and in between this and stuff like that. But in general, what people use are random walks. And so we'll learn about random walks on the next few slides. So the core of this is it's unsupervised or self-supervised. We don't have any labels. We don't have any features. Asking about decoding again. Sure. So the decoding is not anything particularly fancy. It's just saying basically we have these two vectors and we want to say if they're similar or not. So we have the embedding for V, which is some node, and then we have the embedding for U, which is some node. And then we want to take these two embeddings. So imagine this is this is a 100 dimension vector. This is 100 dimension vector. And we want to say if these are similar. And so what the decoder does is it takes both of these and then it just returns us some value, 0 to 1, basically telling us if it's simple or not. So that's the function of the decoder. And so the way that a lot of people choose to do this is with the cosine similarity that you can get from taking the dot product of these. So basically you dot product ZV with ZU, and then that will return you some similarity score, basically. And that's the function of the decoder. And so we want the decoder to match together with this similarity value, which is some, we'll learn about what these similarities can be, but typically you just want nodes that are similar. So if U and V are similar, we want them to have a higher score. And if they're dissimilar, if they're not in close places in the graph, or if they're different for whatever reason, then we want that value to show up lower.
Hey, Ryan, can I add a comment here?
Yeah, go for it.
I think one thing that's not readily obvious from the Stanford slides is if you imagine that we're building a neural network and we're going to use, just like always, we're going to use gradient descent in order to train these weights, okay? And then we're going to yank the weights out, and those are going to be our embeddings, okay? So if that's what ultimately we're going to do, the structure we're going to use to train this, then at the very end of it, we need to have labels so that we have a loss function. And so the labels are going to be this similarity measure, which we haven't said yet. Ryan was just about to get there, but we haven't said yet, what is our goal? What is our similarity? So if you have a similarity function that you define up front, now you've got labels. Okay, but we still need a loss function. How are we going to do that? And so the way you do the loss function is you have to have the decoder return you just a single real number, so that then you can say, here's my loss. Is my similarity score was 0.8 and my decoder said 0.6, and so 0.2 is the difference, and I'm going to use that in my loss function. So I don't know if that helps on a sort of a more mechanical, practical level. Conceptually, yes, it's the similarity, but practically speaking, if we didn't have a decoder, we would have, oh, we have all these great embeddings, but what do we do with them? And so I just wanted to kind of add that part.
Yeah, thanks, Ted. Getting back to this piece. So exactly, it's unsupervised. We don't have any labels at this point. We're just trying to generally learn something out of the graph based on its structure and the way that it's interconnected. And so these embeddings are task independent. We're not teaching it something specific yet. We're just teaching it to create something useful out of the structure of the graph. We want it to learn something that can then be used later for downstream stuff. So later, if you want to do node classification or edge classification or something like that, we want these embeddings to be useful for any of those, for any different combinations. I see a raised hand. Do you have a question?
Yeah, so I have a question that how this form of the decoding changes when the definition of the similarity changes, when the meaning of the similarity changes. So how do we change the decoder, the form of the decoder?
For this, we will keep the decoder basically the same. The decoder isn't actually anything learned. What's learned is the embedding. So we're updating the embeddings, but we're keeping the decoder the same. And then the similarity can be whatever we defined. So the decoder is just, it's basically the operation is we're just saying, let's multiply these together. So nothing is really learned there. What's learned is the underlying embeddings, and then those are adjusted to match whatever similarity function we have. Does that explain that piece?
Okay, yeah, understood. Thank you.
Okay. And we can do things that are more complicated than that, but for now we're just holding it constant as the dot product here. Okay. So basically, we learned about generating these embeddings, and we'll learn a little bit about random walks now. So we have the embedding for a given node. So we have node U, and we've created an embedding for it. And basically what we want to do is we want the embedding here to tell us if it's going to occur on a random walk, and we'll learn more about random walks on the next slide. And we'll use that as our similarity function. So we have this embedding, and we want to say, what is the probability that it lands on various different target nodes? So the example we've been using this whole time is we had that node U, and then we had the node V right next to it. And we want to say, what is the probability that we randomly step on that node V when we started at U? And so we'll define two important functions here. So there's the softmax function. This is common in machine learning if you're doing any sort of classification. The gist of it, without digging too deep into the math, is if you have, let's say you have various different outputs, and you say there's a 20% chance of one option, there's a 60% chance of another option, and then there's another 20% chance of another option. That sums together to 1. And what the softmax will do is it will actually slightly increase that 0.6 odds. And it's in lieu of doing the hard max, which would be just taking that 0.6 option, and it just has some nice math properties that makes it easier to learn from. There's probably a better explanation of that softmax somewhere, but we don't need to dig into it too much. And then the sigmoid, I'll kind of simplify that one as well, where it is a function that smoothly condenses whatever number you input into it to be between 0 and 1, and that can help you represent it as a probability. So if the output of your embedding or something is a value like 50, you can pass it through a sigmoid, and then it will put it close to 1. And if you pass in a value of -50, then it will put it close to 0. So learning a little bit about the random walks that we've mentioned a couple times but haven't seen yet. So we simulate this look at the graph by doing random walks. And the random walks, let's say that we start at this random node, and then we just make random decisions, and we just kind of traverse the graph. And we do this for a fixed amount of walking. So let's say we started this node, we go here. Technically, we have the option to go back here. We can go to 6, we can go to 7, but in just by random odds, we end up going to 8, and then from 8 we go to 9, and then 9 back. And you can see there's all of these different options that we can take. But we'll just sample a whole bunch of random possibilities, and we'll go random directions, and that can encode some information about the structure of the graph. So the thing that we're trying to find eventually is the probability that U and V will co-occur on a random walk over the graph. So we start at node U. What are the odds that we hit node V when we do a random walk like that? We do a bunch of random walks, and we find that on 10% of the time we hit node V, for example. That's what we're trying to predict, and that's what we're representing as our similarity function here. So looking at this, we can see we start at node U, and then what are the odds of hitting V is what we're trying to represent as our similarity function. And so we try to optimize our embeddings to make it so that we can accurately predict this relationship.
Hey, Ryan, just to reiterate, so by choosing whether or not nodes co-appear on random walks as our similarity measure, that's choosing what our labels are. That's choosing what kind of information we're going to wind up encoding into our embeddings. If we chose a different thing, we could get different embeddings. And so if you look at these random walks, you can see you're going to get more information than just your immediate neighbors, because the walks don't just go to your neighbors. They go beyond that over time, right? But you're also not just going to like get random information about nodes super far away from you either. So it's this kind of balance between, I want more than just my immediate neighbors, and depending on how long the walk is, you know, I don't necessarily want information about nodes that are 50 hops away from me, because that's not necessarily relevant to what I'm trying to encode.
Mm-hmm. There's some questions about the length of the walks, and we'll discuss that on later slides. But in general, I would say it's a little bit arbitrary. It's kind of one of those hyperparameters that you can tune depending on how deep in the interactions you want to go. If you have a short walk, then you're only looking at your local neighborhood. And if you have a very long walk, then you can possibly represent something very far away, but maybe you don't actually care about something that's 50 steps away, or that's just too far.
Yeah, and actually what we're going to see is that Node2Vec cleverly designs the algorithm so that this hyperparameter is not as important. If you just use vanilla random walks, then it's what Ryan said. The longer you make the walks, the more you're encoding global structure. And you need to be careful, because imagine you had a small graph with only 100 nodes and you did walks of length 200. I mean, maybe you get the same embedding for every node, you know? But what we'll see is that Node2Vec actually is a little less, I think it's still dependent, but it's less dependent on that length that you choose.
Yeah, so the reason that they've chosen to use these random walks, though, is it actually is really good at representing both the local and the global representation, because we looked at things last time in terms of various different graph metrics like the clustering coefficient and the in-betweenness and different things like that. And these random walks actually give us a really good representation of the structure, and so that's why we use them versus various different things like that, because we could use those things, but they're not very useful in terms of making embeddings. These can represent something that's a bit more complex, and then we can condense it down with the embeddings. And it's also just useful because it's much more efficient. We don't have to compute a ton of stuff. We can just kind of do a little bit of rollout and simulation and then gather a whole bunch of information quickly. And we might not necessarily get the 100% representation of the graph, but we get some sort of approximation that is actually useful to learn from without causing some massive computational expense. So the whole idea with this unsupervised approach is that we want to keep some similarity in these embeddings. We want nodes that are close to each other to occur close in the embedding space. And so we'll look on later slides. This N and R of U is something that we'll look a bunch. And basically the way to read that is the nodes that are part of the neighborhood of U given the random walk strategy. So we will look at this more on later slides. So given a graph G, we have different vertices and edges. and then we want to make some mapping to the embedding space. So the Z of U is basically saying we have some function that takes the node U and then it maps it to some embedding for U. That's how you read that. And then, like I was mentioning, NRU is the neighborhood of U by strategy R. So the way I read that is these, the NRU is the nodes that you will hit given that you start at U doing random walks. So you do a bunch of random walks and you see, okay, we hit V various times, we hit J various times, we hit various different nodes. And what we're trying to do is set it up so that the embedding of U makes it so that the embeddings of these close by ones end up close to it in the embedding space as well. So one of the questions was about the length of the walks. This slide is basically telling us that. So we have fixed length walks, and this is a parameter that we can tune. We can choose 7 or 15 or any other number. And it just depends on, like Ted was saying, the trade-off that we want between the local representation and the global representation. So more steps equals just wandering deep into the graph and maybe not telling as much about the local neighborhood, and having a shorter walk will focus more on the local neighborhood. So I think I'll skip this for now because this slide shows it a bit better. Basically, the way that we're going to train this and gather this information is we're going to sum over all of the nodes U, and then we're going to sum over all of the nodes that are within that neighborhood, the neighborhoods of U. And then we want it to maximize the probability that we get the similarities close between the ones that were actually in the neighborhood and the ones that are low aren't actually in the neighborhood. And we'll talk more in detail about some of these steps. But the way that I look at this is we're kind of iterating across all of the nodes of the graph. So let's say we have 1,000 nodes, and then we have all of the nodes that we hit when we went along these random walks. And we want these to line up such that our similarity is showing high when we do hit nodes that were actually on the walk, and we want it to show as low when we hit nodes that weren't in the random walk. So one of the major problems with this is we're actually doing a sum or in some senses, sort of like a for loop over all of the nodes of the graph inside of each other, a nested for loops over all of the nodes. So this happens because when we're training, we go over all of the nodes in the graph. So let's say you have 1,000 nodes. And then to make this output, we have to iterate over those same 1,000 nodes again and say basically which ones are similar. And this is okay if you have 1,000, but it's actually extremely slow if you have 1,000,000, because you're training a new embedding for every single node in the graph, and you have to also loop over every single node in the graph again to represent the probability of hitting them on a walk. And so on the next slide, we'll look at some strategies to kind of mitigate this. So this big problem is that we're summing over all of the nodes in the graph, and then we're summing inside of that all of the nodes in the graph. So if we have 1,000,000 nodes, we're doing a for loop that's a million long, and then we're doing another for loop that's a million long inside of it, and then we get this massive explosion. So looking at the way that we get past this, we can do what they call negative sampling. And so right now, what we're doing is we're doing that million by a million, and actually in that inner million, most of those are negative cases where it's just these nodes that are way far off in the graph that you never touch on the random walk. And we don't necessarily need to teach the model every single point that isn't connected. We're kind of more focused on the ones that are actually close by. And we can teach it generally, these ones or like many of the other ones are not close, but we don't need to necessarily do a massive loop over all of them. We can just sample over some of them. So rather than doing all 1 million, we can basically do, let's say we hit 20 different nodes on our random walk, and then there's a million different ones that we didn't hit. We can just sample another 20 negatives along with that. So it learns 20 of them were positive, 20 of them were negative. And then in general, because we're doing that across all of the different nodes, it can learn these are the ones that happen next to this node. And then it seems like all of the rest of them don't occur. And this is a bit of a hack in order to approximate this without needing to do that massive amount of negatives. And it's probably good just in terms of learning, because if you have that massive imbalance, your embedding is going to be biased to just learn that nothing is close by. So this probably also speeds up training in some way. So any questions on this part yet?
So Ryan, I don't know if anybody's going to ask, but I had to spend some time noodling over this one. This one confused me for a while. You know, in the original equation, right, in the numerator, we only have the dot product of our node U with its neighborhood. So you want obviously to maximize those. You want those to be as close to 1 as possible. And then in the denominator, we have the dot product with every single other node. So like in your case, 20 in the neighborhood in the numerator and 1 million in the denominator. And so obviously the bigger the denominator is, the worse our score is going to be on our loss function. So what we really want is that number to be as tiny as possible. And so in the optimal case, since it includes your neighborhood, it's all nodes, it includes your neighborhood. In the best case scenario, it's 0 for anything that's not in your neighborhood. And it's the same value, you know, for the ones that are in your neighborhood. So what negative sampling does technically, there's this weird thing on the right-hand side. So if you look at the second line there, you have, you have this node n sub I sampled from, what is p sub b? I don't know, but it's this sampling thing, and it's like, what the heck does this really mean? And so the simplistic thing is, we change this from a multi-class classification problem to, we just treat this like, let's say you say case 20, you treat it as 20 binary classification problems only on things that are not in your neighborhood. And so then your label is 0 because it's binary classification, which is a slight oversimplification, but it's close enough. And so then basically it says for those 20, you just treat it as binary classification with the label 0. So I don't know.
Is it going to be something similar to like 1 versus all kind of thing, like binary classification?
Yeah. So instead of doing this 1 versus all classification, we're just I get confused on the terminology of whatever, but we're just simply going to say, for the nodes that are in the neighborhood, we're just going to say we want the dot product we want the cosine similarity to be 1, okay? The normalized dot product. And then for the ones that are not in the neighborhood, we want it to be 0. And we're not going to bother with the fact that maybe the correct answer should have been 0.001, or maybe for the ones in the neighborhood, it should have been 0.99. We're just simply say, no, we're just going to set the target to 1 for everything in the neighborhood and 0 to everything out. And then as Ryan said, if you're doing this over a million nodes, if you do 20 negative examples for every node, you're going to have 20 million, so to speak, examples in one epoch of going through all the nodes. And so that's a lot of data to tell you, a lot of feedback from the ones that aren't your neighbors. You don't necessarily have to do all 999,980 of them for every single node, right? Because you're going to be getting a lot of signal over and over and over and over again. Yeah, so Martin asked, are they unit vectors? I don't think in this case they're unit vectors. I apologize. I'm talking in terms of simplistic if you had the normalized dot product. And so I think of 1 and 0, but I don't think mathematically they actually normalize them just because it's faster not to bother doing that. So this is a good question, Martin. So I'm being a little loose. I apologize when I say 1 and 0.
So I got a quick question. Where's the sigmoid function? Is that the sigma right after the log? Is that the sigmoid function?
Yes. When you see that little sigma, that's the sigmoid function, and that's actually what has turned this into a binary classification problem, because we're now using sigmoid loss, basically. Okay. And so that was not at all clear to me. I went online and I looked at like 3, 4, 5 different sites before it finally made sense to me, where somebody said, hey, look, we're doing this multi-way classification problem where basically we are predicting a floating point number for all million pairs of you with everything else, okay? And instead we're changing it to say, no, if I have 20 neighbors and let's say K is, you want to use a slightly different number, let's say K is 30. I'm going to turn this into 50 binary classification problems where for my 20 neighbors, I say the target is 1, and for my 30 negative samples that I randomly pick, I'm going to say the target is 0. And that's why it introduces sigma here, whereas before we never had a sigma.
Yeah, and I went back to this slide because I did kind of skim over that. So we were doing the softmax here. This is what this function represents, the exponent and the summation, and then now it's changed to just the sigmoid. That's kind of the major change that's happened here.
Yeah. What I struggled with is at first I thought that this second equation was sort of approximating the first one, but it's not really technically doing that. It turns out there are people who tried to just speed up the softmax, and so they build these like Huffman trees and do stuff so that they can approximately calculate the denominator, which is all million nodes. But this really actually isn't technically trying to do that. It's simply saying, I'm going to do, let's say, 30 nodes that aren't my neighborhood, all the nodes that are in my neighborhood. And when we repeat this process over and over again for every single vertex, we'll eventually get pretty good coverage and the thing will learn.
And Ted, the 30 nodes which are not in the neighborhood, are they connected to the target node U? Or I mean to say, sorry, they should not be connected to the target node.
That's right. So basically, technically speaking, if K is 30, what you do is you pick from the million nodes minus the ones that are in your neighborhood, but you're doing a weighted sample based on the degree of each of those million nodes. So technically, it's not a uniform pick from the other 900,980. You're doing a slightly weighted one where higher degree nodes have a higher chance of getting picked as negative samples.
Okay.
If you know the word to vec algorithm, they actually found that weighting based on the equivalent of degree based on word frequency wasn't quite optimal. And so they actually slightly increased the weight of rare words. And so what they did was they took the word frequencies and they took them to the 0.8, I think, power, which ended up downvoting popular words and upvoting rare words a little bit. I noticed that in this case, they didn't do that extra step. They just simply weighted it by degree. But hypothetically, you could futz with the way you weight the negative samples a little bit.
Actually, I actually came across this NCE, the noise contrastive estimation. Another context was like, a simple multi-class classification done over 1 million classes actually. So somebody had mentioned this technique in a different context, not in graph context actually. Like, let's say you have thousands of classes instead of like, 40 or 60. What happens is that softmax cannot do like probabilities of million classes all adding up to one. So they use this technique in there. I just skimmed over and didn't go deep there. So I think we'll have to go back to that.
Oh, that's cool. So I think that might be what you were saying, Ryan, about it might actually converge faster than trying to do an actual formal softmax over 1 million things.
Yes,
yeah, I want to add a little bit. I think, yeah, that is right. It is the same concept here. And also, when we have this distribution from the encoding and the decoding with negative sample, that's where the algorithm minimizes the cross entropy to get the correct embeddings.
By the way, one other thing I will add is that one of the articles that I read said, let's say you did actually calculate the softmax. You're willing to pay the price, okay? So in your denominator, you did the dot product of node U with every other node, and you summed them, okay? Once you're done calculating your loss, you now need to back propagate that over all million of those nodes that contributed to that loss. When you do this negative sampling, in my case, I said, let's say it's 20 nodes in the neighborhood, 30 in your negative samples, you only have 50 weights that you need to update when you backprop. So it's not just even the calculating of the softmax, but it's also the downstream impact of the backprop. So it really makes a huge difference in computation time.
I think that in the backprop, we could run into the problem of like the vanishing gradient with so many nodes.
Yeah, it's a problem where you're going to have really tiny. You might have some really tiny gradients. Due to the exponentiation. It's not deep. These networks only have one hidden layer. So it's not a problem of depth, but 1 million tiny things being exponentiated and summing them. Yeah, I don't think 32-bit float is necessarily enough for that.
There was another question about the random walks, if it's treated equivalently, if you run across something at distance 1 versus distance 19. And yes, so it doesn't really matter when you occur on something during the walk. It's just whether you hit it or not, basically. But generally, something that's at distance 19 is going to happen less frequently than something that's at distance 1. And so that's going to be reflected in the probability that's returned from sampling all those random walks. So moving on to the next section, gradient descent's already been mentioned a couple times by Ted, but the way we learn this is through gradient descent. And what gradient descent, kind of the simplified explanation of it, is just that we see our similarity, we see what our decoder outputs. So our decoder looks at the embedding for U and the embedding for V, and then we want it to be high because our similarity score says that it's a 1 or something like that. And then we try to push it in that direction if it's not already there. So if our decoder says 0.5 and our similarity score says 0.7, then we'll push it towards 0.7 and vice versa. And so we take the derivative and then we go in the opposite direction, basically pushing it towards the correct answer instead of whatever the cost is. And so in turn, we should be updating these embeddings to push them closer to the right answer over time as we do iterations through them. And so the general case of gradient descent is what I described, but then stochastic gradient descent is when you are looking at individual samples at a time. So there's stochastic gradient descent, and then there's batch gradient descent. Batch is when you do every single one all at once to take one huge step. And people tend to prefer stochastic because you can just make a whole bunch of small iterations, and it makes it learn a bit faster. You don't have to look at everything before you take an individual step. And then there's the in between of that, which people call mini batch, which is basically saying, you can take one sample, you can take all of the samples, or you can take just 8 or 16 or something like that. And that tends to work well because you can kind of smooth out the noise of taking individual samples, but you also get the benefit of some parallel working speed up. So the talking about the initial setup, these embeddings actually start with just completely random values. So if you have embeddings with dimension 50, all of those 50 values are going to be random. And then across all of the nodes, they're going to be initialized different random numbers, basically. And you can define random in various different ways. People have found different characteristics, like is it normally distributed or uniform or anything like that. People have found strategies for that. And then what we'll do is we'll essentially keep looping through this iteration using stochastic gradient descent and updating until we finally get some values that don't seem to be changing very much. So we run through a whole bunch of loops, and then eventually we converge to something where it seems like our similarity score and our decoder output yield similar results, and our overall score isn't changing for that task very much between iterations. So looking at just kind of reviewing random walks, we do these short fixed length walks. We do a bunch of those, and then we say, what's the probability of hitting a bunch of different nodes given that you started at U, and then you optimize to make it so that our embeddings line up such that our decoder says that its neighbors show up with high similarity, and things that are far away that we don't hit in our random walks show up as zeros, most likely.
Hey Ryan, quick
Yeah.
question. How do you decide what's the the target similarity score? Who decides that?
The similarity score, that's derived from the random walks. So that's saying basically we did 100 random walks. There's some node V, and we hit it 50% of the time. So that 50% of the time is your similarity score. It's 0.5. It's saying you started at node U and you hit node V 50% of the time, that's your similarity score under this strategy. There's a bunch of different strategies for similarity score, but random walk and the probability of hitting those nodes is what we're using as the similarity score here.
Okay.
So we talked about random walks, but then we can start looking at maybe there's some better strategy than just completely randomly wandering the graph. So we can look at some biased ways of traversing the graph rather than just randomly. So then the initial approach that we were looking at, people would call deep walk, which is just do the random walk through and then learn those embeddings. But the evolution of that, something that people have found is even more successful, is this node to vec. And the big difference with node to vec is a better strategy for defining what's in the neighborhood rather than just randomly wandering. We can do something a bit more thoughtful that explores in a more structured way. So randomly wandering, we go some amount through the graph. Let's say you go 25 steps. You're just going to end up somewhere random. And depending on the structure of your graph, you'll end up somewhere completely different, and you might not necessarily capture the local structure because you just right from the start, you just wandered away from where you started and you don't actually learn the stuff that's near it. So node to vec introduces the idea of kind of combining breadth first search and depth first search. And so breadth first search is saying we start at node U, and we would say, basically, let's look at all of the stuff that's around it. So let's go to S3, let's go to S1, let's go to S2, and let's stay close to U and just explore everything around it. And then the depth first search is basically saying, let's go in one direction and let's just keep going until we're as far away from U as possible, until we hit some sort of termination or we run out of length or something like that. So using these two strategies is kind of different than just doing random, where we might end up doing something closer to depth first search, but not really intentionally. And so doing both of these more deliberately, we can get better representation of both of these. So like what I was mentioning, you can get the local view and you can get the global view. And so the breadth first search gives you that the local view rather, and the depth first search does the global. It gets you further along the graph and you get to explore further away. So this is what breadth first might look like. So you just explore the 3 nodes near you, and then depth first, you're going 3 nodes away. So in the node to vec strategy, there's kind of 2 different parameters that we can tune. One of them is P, which is how often we return to the previous node. And then the other one is Q, which is sort of a trade-off between depth first search and breadth first search. And the next slide will show this in a bit more detail. So say we start at node S1, and then we travel to W. Then we have various different options. We have the option to go back to S1, and that's determined by P. That was our probability of returning to the previous node. And then we have the trade-off between the breadth first search and the depth first search. And so the depth first search choice would be to go to S3, and the breadth first search would be to go to S2, because this keeps us similar distance to S1, and this gets us further away from S1. So looking at these, this is parameter P is our probability that we return to the previous node. This is one of our options when we're at W and we just came from S1. And then we have Q, which they're calling our walk away parameter. So we define this as going to S3 or going to S4, and then our alternate is staying similar distance. So this, we're still 1 unit away from S1. So this breadth first is going to make us stay or try to stay all of the ones that are 1 unit away, or return back to somewhere we've already been. And the depth first is going to push us away and try to traverse deeper into the graph. So this is just a table showing the probabilities laid out. And then we can also see on the side is the distance from the places from the starting node, basically. And so if we have a low value of P, it's going to make us act more like a breadth first search. And if we have a low value of Q, it's going to make us act more like a depth first search. And this makes sense because breadth first search, when we have a low P value, that's going to make it more likely to return to the previous node. And so we're going to stay in this neighborhood, basically. We're going to keep feeding back to S1, and then we'll kind of traverse everything around it. And depth first search, if we have a low Q, it makes it more likely for us to kind of meander out and go to different places in the graph. So this functions very similarly, where what we're going to do is we'll do a whole bunch of random walks of some certain length L, and we'll do that for every node U. And so we get this massive matrix for every node. We have the probabilities that we hit the other nodes in the random walk, and then we go through and we try to optimize that using the gradient descent to make it so our embeddings represent that probability matrix. So one of the things I wanted to touch on is we doing all of these random walks, we actually yield this massive matrix that tells us the probability of hitting any of the other nodes on the graph. And that on its own is actually very useful. It has a whole ton of information on it. So why would we be motivated to then go make an embedding out of this rather than just using that matrix itself? One of the big advantages of doing that is you're compressing it and you're making it a much more general representation. So when you have it in that expanded matrix form, if you have 1 million nodes, you have a whole ton of different variables, and you're not actually representing in a dense way the information of the network. So if you have 1 million nodes and you reduce it down to 512 dimension embeddings or something like that, then you can pass that to another learning algorithm, and you'll probably have a better representation out of that because it's just much more dense, and kind of repeated structures are encoded in the same place and stuff like that. So you get something much more useful out of it. And at the same time, it'll be more computationally efficient, because if you have these million column vectors, then you're probably going to run into some massive memory usage in terms of like if you pass that to linear regression or any other algorithm, it has to deal with all 100 columns, which is a very sparse representation and might not be good for you. So one of the important pieces of this whole algorithm is all of these pieces you can parallelize pretty easily. You can do the random walk probabilities, you can simulate all of them, and then you can do this optimization stuff all highly parallel. So you're not really waiting on one thing to complete. So there's a bunch of other random walk ideas. I'm sure that people have been iterating on this for years, but I think Node to Vec is still kind of not necessarily a winner, but I would say it's the one that's been popularized, and you can get an easy implementation of it and not have to worry too much about it, because it will probably get you results that are close to leading on that. So I've said this a few times, but the overall idea is we want these embeddings for each of the nodes to be similar for nodes that are similar and far away for ones that are not. And we looked at various different ways of doing this. So the simplest possible approach for measuring the similarity is just saying, is this node connected to this other node? That's one possibility. We looked at that adjacency matrix where it was just 0, 1, 0, 1, and stuff like that, saying which nodes were connected together. And then in the previous chapter, we looked at the neighborhood overlap. So Ted was telling us about all of this stuff, like the interconnectedness and the clustering coefficient and all of that stuff. And then now we've looked at the random walks, which are popular and still used today. So then the kind of general recommendation of what do we do with this information? They say that Node2Vec still performs really well in terms of node classification, but there's a bunch of other methods if we want to do link prediction. So training these Node2Vec embeddings will apparently be good for node classification, but if you're doing link prediction, you might want to consider other options. So one of the things we talked about at the beginning was there's a whole bunch of different tasks that you might want to do. So you might want to do node classification, you might want to do link prediction, you might want to do graph prediction, you might want to do some form of clustering or anomaly detection. And so they're saying for this that it's very good for node classification. And then in the next section, we'll see that it's also good for graph classification. So they're saying random walks are efficient, and we need to define exactly our node similarity. So that's what we've been looking at, the various different strategies for that similarity function, the random walks, the Node2Vec walk that's a bit more structured. Ted, you mentioned you had a notebook potentially for Node2Vec. Is that something you think we have time to show, or should I move on to the graph embeddings?
Yeah, I think it might be nice just to show it. I can do the sort of whatever 3-minute version of it.
Okay.
Okay, so so Ryan and I also have this other book, this packet book that's referenced here, Graph Machine Learning. And so essentially this is just the code that they have in their sample notebook. I've done some minor cosmetic modifications, but shout out to them. These are the packages that they recommend. I'm running this on my local machine, so I apologize. I haven't completely debugged this if you're like running in Colab, if this exactly works. But so just wanted to quickly scroll down and show you for Node2Vec, they create this very extreme looking graph. Okay, so here's a barbell. It has these tight clusters of highly interconnected nodes, and then it has this section in between, this long section that separates these two clusters. I think these are even like full clicks where everything is fully interconnected. All right. So if we run Node2Vec and we do something that's not typical, but we're gonna set the number of dimensions all the way down to 2 because we want to visualize the embeddings that are created. Okay. So it's a relatively small graph. It's like what, 24 nodes? And we're gonna do a small number of dimensions. If we then plot the two values, the Z1 and the Z2, that it comes up with the embeddings, you'll notice that we get a tight cluster of embeddings here, a tight cluster of embeddings here. And what are these ones that are sort of floating not near these other clusters? 10, 11, 12, and 13. That's actually these guys right here. And so it's really just kind of what we would want. Now this, again, is a very simplistic, contrived example, but at least it passes the test on the surface that these nodes had very similar embeddings. These similar, and these guys were sort of dissimilar from both of those clusters. So then what I did is I changed the default value. So I ran with Q equals 1, which is the default. And Ryan said, smaller values of Q prioritize a depth first search. Okay, so it's prioritizing going farther away from your starting point. The more you prioritize going farther away, the more you're likely to hit these nodes in the middle or these nodes even on the opposite end of this barbell. Okay, so then the more similar everything is going to be. So instead of Q equals 1, I ran it again, this time with Q equals 0.08. I did a little bit of fiddling to try and find an interesting value. And now what you see is things are still clustered, but they're a little bit farther apart, okay? So we have this 10, 11, 12 business here, but you'll notice that like 13 and 14 are now not really part of this cluster. They're just sort of, and so just scrolling back up, 13, oh no, sorry, this is 13, this is 14. So it's really, well, 10, 11, 12, 13. So 9 and 14 are the nodes that are sort of at the edges of these clusters. 9 and 14, right? So where did they wind up? You see 9 is here, and 14 is basically indistinguishable from 13. And if I continue to lower my Q value, then you'll see that these clusters begin to really disintegrate, and you just sort of get more similar values for everybody. So it's a contrived example, but I just wanted to show that that tuning parameters really do kind of let you choose between how local, how global you want Node to Vec to do your embeddings. And we'll post the link to this notebook if you just want to play around either with different graphs or with the parameters.
So one of the, can you pull that up for a second again?
Sorry.
So one of the things I kind of want to point out, can you scroll up to the original node visualization, the up higher before the embedding? Yeah. So if we already have this graphic, we've already laid it out in XY position, we can already see which ones are close. It seems like almost a waste to then do the embedding and look at the visualization, and then you go, oh, look, it's almost exactly the thing that we already drew. We didn't have to learn anything for this. But the thing I want to point out is that there is already some algorithm that has determined how to lay that out on the page. But if we want something higher dimensional, then we need to do that node to vec encoding. So in 2D, we're probably going to end up something that looks similar to that visualization, but it can only represent a very shallow level of similarity. So if we do a different dimension size, say like 512, and we have a much bigger graph, then we can get a much deeper look at the similarity. So right now, that what's already created by Network X shows us something that's similar to what we get from Node to Vec, but in reality, we'd probably do more dimensions and we'd get a deeper look at it than just that 2D view.
Yeah, that's a good point. Yeah, and drawing graphs is hard. So it's just because this is a very trivial looking graph, it actually did a pretty decent job drawing it, but no guarantees, even with a, I don't know, 200, which would be pretty tiny, 200 node, that you'll see anything other than just a blob.
I will take back screen share. So everyone can see the slides again. I just want to make sure okay. Yep. So in the first section, we were looking at the embedding of nodes, and then now we'll be looking at the embedding of entire graphs. So just kind of reviewing before, we were looking at, we've got this node U, we want to make an embedding for it. So what do we do if we want to get an embedding or some representation for this entire graph? We probably want to embed it again, but what technique do you do to actually create that? So we might want to do that for classifying toxic or non-toxic molecules, or we might want to do anomalous graphs, or we might want to find which graphs are similar, or various different things like that. And so the simplest possible approach is actually we do the node embedding that we've already learned about, and then we just find some aggregation function for it. So we go back to this graph and we say, okay, we have the node embeddings for every single node inside of this graph. Let's just take the sum of it, or let's take the average, or let's aggregate it in some other way like that. And that can tell you some representation of the entire graph, but it's probably not necessarily the best one, because all you've done is you've taken the sum and you don't really know the deeper interactions than that. So that's what this slide is showing, is just basically you can take the sum of the nodes and that will give you something, and it will be informative, but it's probably not the best approach. But maybe it's a starting point if you do have a problem that needs that. One of the evolutions beyond that is introducing what they call a virtual node. So you want an embedding for one of these nodes that represents the entire graph, and so or a subgraph within a graph. So what they can do is you add a new node, and then you interconnect it to all of the things that you are interested in representing. So they have this virtual node, they connect it to all of this subgraph, and then they run the same node2vec thing, and then they say, okay, pull out the embedding for this piece, and that will represent this entire subgraph. Or alternately, if you want to represent the entire graph, you just say, make this virtual node connect it to everything on the graph. So it's this kind of global point that just represents the interactions of everything. And then you can extract the embedding from that, just doing the normal node2vec and then pulling out the specific one that you created called the virtual node. And that will probably be more useful to you than actually taking the sum, but there's still another representation beyond that. So one of the things that gets introduced in the next evolution of that is these anonymous walks. So we looked at random walks. Now we'll do random walks, but we'll also anonymize them. So the idea here is, imagine that we have some graph, and then we start and we take 5 steps, and we start at A, and then we go to B, we go to C, we go back to B, and then we go to C again. And so the way we run this is we index every new node that we hit, and we don't count it separately for each node. We just basically are counting. So we start at A, that's a new one, so we'll count up to 1. We go to B, and then that counts us up to 2. And then we'll go to C, and that counts us up to 3. But then we go back to B, but we've already been to B before, so we'll say that's 2 again. And then we go to C, and then that's back to the 3rd point that we've been to before. And so this is good under one starting node, but it's also good under other starting nodes. So before we started at C or at A, and then this time we're starting at C, but we're following the same kind of pattern of we're going 1 to 2 to 3, back to 2, and then back to 3. This is the same kind of walk. Walk 1 and walk 2 are following the same kind of pattern, even though we're not starting and landing on the same nodes. And so if we look alternately at random walk 3, you start at A, you go to B, you go back to A, you go back to B, and then you go to D finally. And so that ends up with 1, 2, 1, 2, 3. And so this is a different walk than these two. These two are the same anonymous walk. This is a different anonymous walk. And so this is sort of just the representation of what I just showed there. yeah, we'll just skip that for now. So with these anonymous walks, there's only a certain number of possibilities. So we're kind of compressing what's there. So like looking at something that only has length 3. So if we do an anonymous walk of length 3, there's only a few different options. We can start on one and stay on one the whole time, or we can move to one and then stay on one the whole time, go to 1 1 2 1 2 1 1 2 2 1 2 3. For example, there's only a few possible options. But as you grow that walk, there's exponentially more possibilities. So if you do a anonymous walk of 12, there's actually 4 million or so possible combinations. But this is still less than you would get if you did the non-anonymous walks, the random walks that we were doing before, because you would have had something where you started on A, you go to C, you go to D, and then every time you're doing that on a new graph, it would be completely new points. So these anonymous walks, what they're telling you is kind of the structure of the graph in some way. So for example, if you had a graph that was just a whole bunch of points that are only connected to one other point. So let's say you just have a line and it's just A, B, C, D, E, F, G, and none of them are actually interconnected. They're only connected to the one next to it. That would show up very differently in the anonymous walk distribution than, for example, something that's like hub and spoke, where you have A and then it's connected to all of A through G. So that's kind of what those anonymous walks are representing, and you're trying to get it to generalize across all of the different graphs. So we can follow a kind of similar procedure that we've done in the past with the random walks. You do a bunch of anonymous walks, and you can do that across a bunch of different graphs, and you'll extract something out that's useful, because we'll get this same output on each graph. If you do walks of length 3, then you'll get the same 1 1 1 1 1 2 1 2 1 1 2 2 and 1 2 3, for example. Whereas if you were trying to do the non-anonymous walk across multiple different graphs, you would just get completely different representations that didn't have any carryover. So you couldn't really compare apples to apples. So one of the things that's important with random walks is you probably have to sample a decent number of them to get a good representation of the graph and its structure. So they have this calculation here that basically tells you, with a certain amount of uncertainty, you have these parameters epsilon and delta that can define how much uncertainty you're willing to have in these anonymous walks, and how many you need to reach those parameters. So if you're doing walks of length 7, there's 877 different possibilities, and you want to do this many to reach this sort of uncertainty threshold with those 2 parameters, which seems like a fairly high number to me, but I haven't worked with these much, so I don't know if that's actually high in practice. So one of the things that we can do with that is we can directly use those as features. So the probability of all of the different random walks for a graph could be your features right there. So for example, you have some embedding for a graph that's length 5 if you're doing length 3 walks. And it would say like 0.2 for this, 0.3 for that, and so on, and it would add up to 1. And so the probabilities of hitting all of these different anonymous walks across 100,000 walks would tell you something about that. So then the evolution of that is we can do embeddings on top of that. So rather than, it's like we were doing with the nodes, rather than doing embeddings of the nodes, you do embeddings of the walks, and then you have a bit more flexibility. Like we saw, if you do length 14 walks, that ends up an embedding size of 4 million, and that might not be what you want. You might want something more dense than that. So you can do an embedding on top of these walks. This is where things get a bit more fuzzy to me. So I won't feign any confidence in this part. I need to learn this a bit more to talk about it. But basically, my understanding of it is you rather than doing embeddings on the nodes, you do embeddings on the walks. And so we have this equation here, and before our target was the nodes that occurred on our walks, and instead we're looking at the walks that we would potentially hit, given that we started at a certain node. So before, it was basically this setup that you start at node U, and then you see all of the different nodes that you would hit if you did a bunch of random walks. Instead, what this is saying is you start at node U, what's the probability of hitting all of these different random or anonymous walks potentially? And so if we do the case where you have 14 different or a length 14 anonymous walks, you end up with that 4 million blow up again. And so you would probably want to do that same sort of negative sampling thing. So if you have long anonymous walks, then you do that same negative sampling, and it solves the same problem that it does when you're doing the nodes, where you have a lot of different nodes that you could map to and predict against. So on top of that, we have one piece, which is the embedding for the anonymous walks, and we also have an embedding for the graph, because those are going to look a little bit different between every graph, which node you're starting at and which anonymous walks you'll hit. And so this additional graph embedding is an embedding saying basically which graph we're looking at currently will also guide our predictions. So for example, they have this architecture here where they're showing, here's the embeddings for all of the different anonymous walks that you could hit. And then here's the embedding for the graph that we're interested in. And then we'll either do some averaging or concatenation. And then we do some prediction of what probability we have to hit these other anonymous walks. And then we pass that back through the whole network, or not the network, but rather the embeddings. And then those embeddings will get updated here. And so we'll get a graph-wide embedding, and then we'll get the embeddings of the various different anonymous walks that we can experience. So to summarize the sort of overall graph embedding idea, we can use our node embeddings and we can just sum or we can average them, or we can do that virtual node trick that I was showing earlier. You inject a node and you just connect it to everything you're interested in, and then you run the same node-to-vec algorithm. Or you can do the anonymous walk embeddings, and then you can also concatenate that with a graph embedding that will tell you something that's sort of macro to the whole graph. I think at this point we'll call it there. I think that's what we have time to discuss. Are there any questions? Anywhere I should go back to?
That was good. Thanks, Ryan.
Hey, Ryan, can you go back to the probabilities like about 10 slides back?
This one?
No, even before, like you were showing those S1, S2. Yeah, this one actually. I was like kind of curious. How come when you go from W to S2, the probability is 1?
I was a little bit confused by that as well. But the thing that you have to think about is that this it's kind of, in a sense, the last one left out. So this value doesn't directly need to be changed to change the odds of it occurring, because we're changing the odds of all of these as well. So it sums up so that this one can stay in place, but it's changed by the values of Q on all of the other values and the 1 over P, for example. So we, in theory, Q could also affect this in some way, but it doesn't really have to, because Q is already affecting these options and P is affecting the other possible option that we have. And so these probabilities have to eventually be normalized and sum up to 1. So this one staying constant isn't really meaningful in any way.
Yeah, just to be clear, there's 3 kinds of nodes it considers. The node that you just immediately came from, your neighbors that are the same distance as the node you just came from. So in other words, nodes that are connected to both you and the node you came from. And that's what S2 is. It's a node that is connected to both you and where you came from. So it's the same distance away from your starting point, so to speak. And then there's nodes that are farther away that are not connected to the node that you immediately came from. And so that's why S3 and S4 are considered farther. Now, of course, you could be doing some giant circle so that at some point S3 and S4 might be closer to your original U, but nevertheless, they are farther away from where you immediately came from.
But I thought, like if we are at W, then W to S2 and W to S3, I'm going to say all these 4 probabilities should add up to 1.
They will. So you have the probability that you return to S1, the probability you go to any of the nodes that are also connected to S1, which in this case it's only one of them, S2, and then the probability that you go to a node that's quote unquote farther, so S3 and S4. So then you have 1 over P, 1 over Q, 1 over Q, and then you have to normalize so that they all add up to 1.
Oh, okay.
So the probability of going to S2 is actually 1 over the sum of all of these options. So if we adjust Q to be small, and then this ends up being 2 or 5 or something like that, then that in turn makes this less likely, because it's still 1, but it's out of a bigger total sum.
Yeah, the little green text under that middle column says it's the unnormalized transition probability. So technically, you have to divide everything by the sum of that column so that they add up to 1.
Oh, okay. Okay. Yeah, but it's kind of seems like a little weird that the probability is 1 there. Yeah.
Yeah, it's not actually, yeah, it's an unnormalized probability. It's really a weight. And then once you normalize it, then it's a probability. So that's a good point. It's not technically, shouldn't be called a probability yet.
Yeah.
So the key thing though is that you have these 2 levers that you can either go backwards, sort of sideways, or forwards. And so by adjusting P and Q, you adjust how much you weight going back, going forward, or going sideways. All right, well, I think we'll call it a wrap here. Thanks for everyone for sticking with us with some of the technical difficulties and switching Zoom links and all of that. So we appreciate you surviving that. And then of course that also put us a little bit behind. So at this point, we're gonna wrap up the book club. Yeah, thanks Ryan. Thanks. That was a great tour.